Welcome to Talk Tensors.
Glad to be here for this one.
Yeah, if you have been anywhere near the machine learning community online this week.
Oh, it is literally everywhere.
Right, whether you were scrolling through X or, browsing the ML subreddits.
Or Hacker News.
Yeah, Hacker News is completely blowing up over this new paper that just dropped.
It's massive.
It is. We are diving into a trending topic today that is fundamentally shifting how the field thinks about open weight models, parameter redundancy, and model merging.
The discourse right now is basically comparing this to a video game cheat code.
Yes. People are literally comparing language models to the protagonist in Super Mario absorbing an item to gain a superpower.
Which is honestly a pretty accurate analogy for what's happening mathematically.
It really is. Researchers have essentially formalized a way to allow language models to instantly absorb entirely new capabilities from other models.
Like complex mathematics.
Or sophisticated coding syntax.
Or intricate instruction following.
Exactly. And doing all of this without any multitask retraining and without requiring a massive cluster of GPUs, you are looking at flawless capability merging happening on a standard CPU.
The implications for the open source ecosystem are absolutely staggering. To cut right to the core insight of this research, we're looking at a hyper-efficient manipulation of what are known as delta parameters.
Right.
By isolating these specific weight updates that occur during supervised fine-tuning and applying a highly unintuitive but, mathematically elegant technique called drop and rescale.
DARE for short.
Right, DARE. Researchers have proven you can eliminate up to 99% of these fine-tuned parameters.
99%.
You can wipe them out completely and then seamlessly merge multiple different models together. You are essentially stripping away the dense overlapping parameter interference.
Keeping only the absolute bare minimum mathematical essence of a learned skill.
Exactly. And combining it with other specialized skills to create a unified, highly capable model.
Okay, let's unpack this, because for anyone who has ever wrestled with catastrophic forgetting or, the sheer compute cost of multitask learning.
It sounds dangerously close to magic.
It really does. So to truly understand why the timelines are lighting up right now, we need to map out exactly what we are going to cover in this deep dive.
Let's do it.
First, we're going to explore the state of the art before this innovation. We need to look at the mathematics of parameter interference and why simply adding two models together has historically been such a massive headache.
A huge headache.
Then we are going to dissect the exact architectural mechanics of DARE. We will dive into the staggering benchmark results across GLUE, GSM8K, and human evol, and look at the underlying scaling laws that make this possible.
And we can't forget the philosophical side.
Right. Finally, we will analyze the profound implications this has for the unlock versus learn debate in fine-tuning, and what it means for the future of decentralized AI.
There's a packed agenda.
And as always, a link to the original paper is right there in the description for you to follow along with the data. So let us set the stage. Before DARE entered the chat, what was the structural reality of adding specific skills to these base models?
Well, if we look at the standard pipeline that the entire industry has adopted, supervised fine-tuning, or SFT, is the bedrock paradigm.
The default.
Right. You take a massive pre-trained base model, something like a Lama 2, a Mistral, or even an older encoder architecture like Roberta.
Models that have already learned the general statistical distribution of human language.
Exactly, through self-supervised learning on trillions of tokens. But as we know, base models are essentially just incredibly powerful document completers.
They just predict the next word.
Right. To align them into a useful chat assistant or a specialized coding model, you perform SFT. You compute gradients and update the weights based on a highly curated dataset of instruction response pairs.
So you're tweaking the brain.
Yes. And the critical concept here is the delta parameter. When SFT concludes, the physical difference between the new fine-tuned weight matrices and the original pre-trained base matrices is the delta.
So mathematically, it is just the SFT weights minus the base weights.
Exactly. That resulting delta matrix contains the exact quantified shift in the model's representations that corresponds to the newly acquired skill.
Right, so the delta matrix is basically the isolated topological map of the fine-tune.
That's a great way to put it.
Everything that makes a Python specialized model different from the raw base model exists purely within those delta parameters.
Purely in the delta.
Now, logically, the community looked at this and thought, well, if I have a delta matrix for math and a delta matrix from the exact same base model for coding.
I should be able to just mathematically combine them.
Right, because we want to avoid going back to the drawing board to build a massive, perfectly balanced data set of math and code and retraining from scratch.
Which costs hundreds of thousands of dollars in compute.
Right, so the field started aggressively pursuing post-training model merging.
And that pursuit birthed several fascinating, albeit flawed, methodologies. Researchers developed average merging,
Which is exactly what it sounds like.
literally taking the arithmetic mean of the weights.
Yeah.
Then we saw the rise of task arithmetic, which is a bit more sophisticated.
How does that one work again?
Task arithmetic isolates the delta parameters we just discussed, multiplies them by a specific scalar hyperparameter to control the strength of the task vector.
Like turning up a volume dial on a specific skill.
Precisely. And then it adds them back to the base model. There were even highly complex approaches like Fisher merging.
Oh, right, where they compute the diagonal of the Fisher information matrix.
Yes, for each model, to estimate the importance of each parameter, the idea was to do a weighted fusion, prioritizing the weights that the Fisher matrix deemed most critical to the specific task's loss landscape.
But despite all that sophisticated math, there is a fundamental physical barrier that the community kept slamming into, right?
A massive barrier.
Because if task arithmetic or Fisher merging solved the problem perfectly, this new paper wouldn't be dominating the discourse.
Exactly.
When you attempt to fuse a math delta and a coding delta using these existing methods, the merged model usually ends up degrading. It becomes worse at math than the standalone math model, and worse at coding than the standalone coding model.
It's extremely frustrating in practice.
What exactly is going wrong at the vector level there?
The issue is a phenomenon known as parameter interference. You have to visualize the sheer dimensionality of these networks.
We're talking about matrices with billions of parameters.
Billions. When you mathematically add or average the dense delta parameters of two different specialized models, those weight updates inevitably conflict in the high-dimensional space.
They step on each other's toes.
They do. For instance, a specific weight in a specific attention head might have been pushed in a positive direction during the math fine-tuning to route numerical logic.
But pushed in a negative direction during the coding fine-tune to enforce strict Python indentation.
Exactly. When you average or add them, you either neutralize the weight completely or you push it into a region of the loss landscape that satisfies neither task.
So the resulting representations just become muddy.
Very muddy. The activations are pulled in contradictory directions, and the model's performance inevitably degrades.
Which perfectly sets up the core innovation of this week's discourse, the architecture of DARE.
Drop and rescale.
When you read the methodology section of this paper, the proposed solution to parameter interference sounds almost absurdly simple.
It really does.
To the point where I genuinely questioned if it could possibly work. Let's walk through the two distinct operations applied to the delta parameters.
Step one is drop.
Right. You take this dense delta parameter matrix, the specific hard-earned weight updates that the model learned during SFT, and you apply a random mask to it.
You set a massive portion of those delta parameters to absolute zero based on a drop rate the authors denote as P.
And we are not talking about trimming a little fat here. The researchers are dropping 70, 89.
And in some cases, 99% of the delta parameters.
It is a staggering proposition to digest because from a traditional machine learning intuition standpoint, you just spent massive amounts of compute traversing a complex loss landscape to find the optimal weight updates for a new skill.
And the very first step of DARE is to blindly, randomly delete up to 99% of that optimized knowledge.
If you just did that and stopped, I have to imagine the model would completely break.
The performance would absolutely collapse. If you just drop 90% of the weights, the model becomes functionally useless.
Right.
And that is where the second step, the rescale operation, comes in. And it is the absolute crux of why this works.
Okay, lay it out for us.
After you have ruthlessly sparsified the delta matrix, you take the surviving delta parameters, the ones that were not zeroed out, and you multiply them by a specific scaling factor.
And that factor is mathematically defined as 1 divided by 1 minus p, right? Where p is your drop rate.
Exactly. So if you drop 90% of the parameters, p is 0.9. 1 minus 0.9 is 0.1.
1 divided by 0.1 is 10.
Therefore, you take the surviving 10% of the weights and you multiply their scalar values by 10.
Wait, I need to pause you right there because this is where the counterintuition really kicks in for me.
It's a trip.
How does scaling up a random 10% of the weights mathematically compensate for the fact that we just wiped out 90% of the network's specialized tuning?
It doesn't seem like it should work.
You can't just multiply the survivors by 10 and expect the neural network to suddenly remember the structural information it just lost. What is actually happening to the vectors here?
What's fascinating here is the underlying linear algebra, specifically concerning the expected value of the representations. We have to think about what a linear layer in a transformer is actually doing during a forward pass.
It is multiplying an incoming activation vector by a weight matrix.
Right, to project that vector into a new representational space. The delta parameters contribute a specific mathematical expectation to that output projection.
Okay.
If you randomly drop a percentage p of the weights, the magnitude of the output vector drops proportionally.
The signal decays.
The activations shrink, and the model's internal representations drift entirely off the manifold. However, by multiplying the randomly surviving weights by exactly 1/1 minus p.
You are perfectly preserving the mathematical expected value of the original unpruned matrix multiplication.
Precisely. So because the dropout mask is applied completely uniformly at random across the matrix,
the overall statistical distribution of the weight updates remains intact, just radically sparsified.
yes, and by scaling the magnitude of the survivors by the exact inverse of the drop rate, the total summed activation signal passing through to the next layer remains statistically identical to what the dense unpruned model would have produced.
That is wild. So to the subsequent layers of the neural network, the incoming activation signal looks structurally and dimensionally indistinguishable from the signal it would have received from the fully dense delta matrix.
The expected value of the outputs remains mathematically equivalent.
You have achieved extreme sparsity, drastically reducing the physical footprint of the fine-tune without actually destroying the structural geometry of the embeddings that the layer is trying to compute.
It's brilliantly simple once you see the math.
Now, I know exactly what some of the more seasoned engineers listening are shouting at their devices right now.
They're saying we've seen this before.
Exactly. They are looking at this drop and rescale math and saying, hold on, random dropping and multiplying by 1/1 minus p? That is literally just the dropout formula.
And they aren't wrong. The arithmetic operations are identical to the classic dropout paper from 2014.
But the context here completely changes the game. We need to clearly delineate how DARE fundamentally differs from the traditional dropout regularization technique we use during training.
It is an incredibly important distinction because confusing the two misses the entire novelty of the paper. While the arithmetic equations match, the target and the timing are entirely different.
Right. Dropout is a regularization technique utilized dynamically during the training loop.
Correct. During a forward pass in training, dropout randomly zeroes out the activations, the outputs of the neurons.
To prevent the network from developing brittle co-adaptations and overfitting to the training data.
Yes. And then during inference, dropout is turned off entirely.
DARE, conversely, operates completely post-training.
Exactly. It never touches the activations. It permanently zeroes out the physical delta parameters, the actual weights of the model.
Furthermore, DARE is a static, offline mathematical transformation.
It requires zero access to the original training data.
Zero gradient calculations.
And zero GPUs. It is a one-time matrix operation performed on the weights after all training has concluded.
And the computational efficiency of that is wild. You are permanently altering the fundamental capability structure of a large language model using basic matrix arithmetic that you can execute on a standard MacBook CPU in seconds.
It democratizes model manipulation completely.
Which brings us to the actual empirical evidence. Let's talk about the astonishing reality of extreme redundancy in these models, what the researchers have dubbed the 90 to 99% phenomenon.
The breadth of the experiments here is what makes the claim so robust.
They didn't just test this on one specific architecture.
No, they evaluated encoder-based models like BERT and Roberta,
which are foundational for natural language understanding and classification tasks.
They also evaluated modern, massive, decoder-based generative models like Llama 2 and Code Llama.
And the results were universally mind-bending. Across the board, regardless of the architecture or the specific task, the delta parameters generated by supervised fine-tuning proved to be hyper-redundant.
The data definitively shows that DARE can effortlessly wipe out 90% of the delta parameters without triggering any statistically significant drop in performance.
The rigor of the evaluation benchmarks truly cements the finding, too. For the encoder models, they utilized the GLUE benchmark.
Now, for our listeners, GLUE isn't just a simple multiple choice test.
Right. It is a notoriously rigorous suite of natural language understanding tasks. It includes things like the corpus of linguistic acceptability to test syntactic knowledge,
The Stanford Sentiment Tree Bank.
and complex natural language inference datasets like MNLI and RTE, which require the model to understand nuanced logical entailment between sentences.
It is a very sensitive benchmark.
For the decoder models, they used applicable to measure open-ended instruction following against GPT-4 as a judge,
For mathematical reasoning, they used GSMA-K and the math dataset.
which are incredibly unforgiving.
Extremely. Because autoregressive generation requires strict, flawless logical steps to reach the correct final integer. A single hallucinated token ruins the entire output.
And for the coding models, they utilized MBPT and OpenAI's Human Eval, which test actual executable Python generation.
Across all of these diverse, highly sensitive benchmarks, the models retain their specialized capabilities even when 90% of their fine-tuned weights were zeroed out by DARE.
And if dropping 90% seems unbelievable, the data reveals an even more fascinating dynamic when you push the algorithm to the absolute brink at a 99% drop rate.
This is where it gets really theoretical.
There is a clear scaling law of dropping weights that emerges here. Let's look at the ablation on the wizard math models.
These are models built on the Llama 2 architecture, specifically fine-tuned to solve complex math word problems.
Right. They tested 3 different parameter sizes, a 7 billion parameter model, a 13 billion parameter model, and a massive 70 billion parameter model.
And when you evaluate them on GSMA-K and start turning the dial on the DARE drop rate, an incredible pattern appears.
At a 90% drop rate, the 7B and 13B models hold up just fine.
But when you push DARE to a 99% drop rate,
The 7B and 13B models hit a mathematical wall. Their internal representations collapse, and their accuracy on the math benchmark falls off a cliff.
however, the 70 billion parameter wizard math model takes that exact same 99% drop rate flawlessly.
Its accuracy barely fluctuates. It remains just as capable as the fully dense 70B model, even with 99% of its delta parameters permanently deleted.
It's incredible.
So what does this all mean? Why does the massive model survive the aggressive pruning while the smaller models shatter?
If we connect this to the bigger picture, what we are observing is a powerful empirical validation of the lottery ticket hypothesis and the deep implications of LLM scaling laws.
Okay, unpack that for us.
The data clearly suggests that larger network capacities naturally tolerate significantly higher levels of sparsity. As you scale a neural network up to 70 billion parameters, the internal dimensional space becomes massively overparameterized.
So the model possesses so much raw representational real estate that the specific structural knowledge it acquires during supervised fine-tuning isn't stored in a localized fragile cluster of weights.
Exactly. Instead, it is distributed across a vast, highly redundant, high-dimensional manifold.
Because the task-specific routing is so incredibly diffuse and redundant across billions of parameters.
You can surgically drop an astonishing 99% of the delta updates, and that surviving 1% once rescaled to preserve the expected magnitude still provides enough directional influence to route the activations correctly through the layers and solve the complex math problem.
Right. While the 7 billion parameter model, while capable, simply does not possess that sheer volume of representational redundancy.
Its fine-tuned knowledge is forced into a more concentrated vector space,
making its structural integrity more fragile when pushed to extreme sparsity levels like 99%. That concept of massive overparameterization leading to extreme sparsity is the master key that unlocks the real magic of this paper solving the model merging problem for real-world localized deployments.
Because we established at the start of the deep dive that the historical gap in the field was parameter interference.
Right. When you try to merge two specialized models, their dense weight matrices step on each other's toes in the high-dimensional space. So let's connect the dots here. How exactly does applying DARE practically eliminate parameter interference?
It is the ultimate expression of less is more, operating purely on geometric probability.
Okay.
Think about the physical space of these parameter matrices. If you have a fully dense delta matrix for Python coding and a fully dense delta matrix for mathematical reasoning, and you attempt to mathematically overlay them through simple addition.
Virtually every single parameter coordinate has competing non-zero values. They conflict almost everywhere.
Exactly. However, if you apply DARE, and strip away 90 to 99% of the delta parameters from both models before you attempt to merge them, those dense matrices become incredibly sparse.
They are now predominantly zeros.
Consequently, when you overlay the highly sparse math matrix and the highly sparse coding matrix, the geometric probability of a non-zero parameter existing in the exact same coordinate position in both models drops to near zero.
You have effectively eliminated the physical overlap within the vector space.
The models no longer step on each other's toes because they are literally no longer occupying the same dimensional coordinates.
They're essentially operating on entirely separate, non-overlapping subnetworks woven within the massive shared architecture of the base model. It is brilliant.
And because of this zero interference property, DARE acts as the ultimate plug-and-play pre-processing module for all the existing merging techniques the field has already developed.
So you don't have to throw away task arithmetic or ties merging?
No, you just run the models through DARE first. Let us examine how it specifically synergizes with existing methods. Take task arithmetic, which we discussed earlier.
It takes the delta parameters, multiplies them by a scaling term, and adds them to the backbone.
But historically, it suffered from severe interference degradation. By inserting DARE into the pipeline, you simply sparsify the deltas first.
You run DARE on the math delta, you run DARE on the code delta, and then you use task arithmetic to add those sparse matrices together.
Exactly. And the improvement is even more pronounced with ties merging.
Right. Ties merging was a complex method designed to resolve interference by explicitly trimming low-magnitude parameters and resolving sign disagreements.
For instance, if the math model wants a weight to be positive, but the coding model wants it negative, ties elects the dominant sign.
But the inherent flaw in ties merging is that its initial rigid magnitude trimming phase almost always causes a drop in baseline performance.
However, when you introduce DARE, you have already safely eliminated 90% of the redundant parameters through random dropping and mathematical rescaling.
Which we know preserves the expected value without performance loss.
Right. Ties merging then seamlessly operates on these already sparsified deltas, treating the zeros as the smallest magnitude.
This elegantly bypasses the destructive nature of Tie's usual trimming phase,
allowing it to focus purely on resolving the incredibly rare sign disagreements that might occur in the remaining 1 to 10% of overlapping weights.
And the benchmark results for this unified merging pipeline are where the community really started paying attention, because we aren't just talking about maintaining performance anymore, we are talking about active synergy.
That is the truly novel discovery of this research.
Let's detail the specific experimental setup the researchers engineered to prove this. They selected 3 distinct 13 billion parameter models.
Crucially, they were all homologous.
Meaning they were all fine-tuned from the exact same Lama 213B foundational base model. The first was Wizard LM 13B, a model specifically aligned for general instruction following and conversational chatting. The second was Wizard Math 13B, rigidly specialized for mathematical logic.
And the third was a Code Alpaca 13B model, optimized for generating executable Python code.
The researchers applied DARE to sparsify the deltas of all 3 models and then merge them into a single set of weights using task arithmetic. The results are, frankly, staggering.
They really are.
Merging these decoder models with DARE plus task arithmetic didn't just match the performance of the 3 standalone source models, it actively improved upon them in several critical domains.
Prior to this, model merging was always viewed as an exercise in compromise. You accepted a 5% degradation in coding ability to gain a 5% boost in math.
It was a zero-sum game.
But with DARE, the synergistic effects are undeniable. Let us look at the empirical data. When evaluated on AlpaCival for general conversational capability, the standalone Wizard LM instruction model scored 67.20. When they merged all 3 models, the language model, the math model, and the code model, using DARE and task arithmetic, the score actually jumped to 69.28.
That is a positive 3.10% absolute boost in general instruction following capabilities simply by absorbing the sparse, non-interfering math and code subnetworks.
And it gets even wilder on the specialized coding benchmarks.
The standalone Code Alpaca model scored a 27.60 on the MBPP code generation benchmark. But when they merged the general Wizard LM model and the code model using the DARE pipeline, the MBPP score skyrocketed to 33.00.
That is a massive positive 19.57% relative jump on a strict coding evaluation compared to the standalone code model.
This proves the models are actively helping each other. The general linguistic reasoning and structural understanding of the wizard LM model is synergizing with the strict syntax knowledge of the code model.
And because DARE completely mitigated the parameter interference, the merged entity becomes significantly smarter and more robust than the sum of its distinct parts.
Furthermore, we must emphasize that this isn't just an isolated, carefully curated laboratory curiosity. This technique has translated directly to topping highly competitive global leaderboards.
The researchers wanted to validate DARE's efficacy in the wild.
So they utilized it to create two merged 7 billion parameter models, which they affectionately named Super Mario V1 and Super Mario V2.
Let us look at the construction of Super Mario V2. They took two highly performant, different open-source 7B models, Wild Macaroni and West Severus.
Both of these were homologous, having been fine-tuned from the Mistral 7B foundational backbone.
They applied a 50% DARE drop rate to both delta matrices and then merged them.
The real-world validation was absolute. Super Mario V2 actually hit rank #1 on the incredibly competitive Hugging Face Open LLM leaderboard for all 7 billion parameter models.
It achieved an average score of 75.49 across a brutal gauntlet of diverse evaluations,
including the ARC Reasoning Challenge, Hellaswag for Common Sense Inference, the massive MMLU benchmark, Truthful QA, 100 and GSM-8K.
It beat out heavily funded, custom-trained models from major labs.
And it achieved this dominance entirely through offline CPU-based parameter merging without training on a single new token of data.
It's a true paradigm shift.
Here's where it gets really interesting, because the hallmark of a truly great machine learning paper isn't just publishing the state-of-the-art results and calling it a day.
You have to show your work.
The researchers conducted rigorous ablation studies to prove exactly why the internal mechanics of DARE work, and more importantly, to demonstrate what happens to the vector space when you break their rules.
We need to talk about why the rescaling step in DARE is absolutely mathematically non-negotiable.
What exactly happens if you just randomly drop the parameters and you completely ignore the rescaling formula? The researchers tested this exact scenario and labeled it the drop and leave baseline.
The drop and leave baseline is critical for understanding the mechanics of neural representations in high-dimensional space. If you randomly drop 90% of the delta parameters and you fail to apply the 1/1 minus p scaling factor,
the model's internal logic breaks down completely.
The researchers proved this empirically by analyzing the cosine similarity of the embeddings across the network's layers.
For our listeners, in a transformer network, the embeddings are the high-dimensional vector representations of the input tokens as they are processed through the hidden layers.
The direction of these vectors is everything. It dictates the semantic meaning and the logical routing of the data.
You want the layer embeddings of the pruned model to have a very high cosine similarity, meaning the vectors point in the exact same direction in the high-dimensional space as the embeddings generated by the original, dense, unpruned model.
Right, because if the vectors start shifting their angles and pointing in different directions as they pass through the layers, the model is misinterpreting the data.
The attention mechanisms will route information incorrectly, and the model will either hallucinate wildly or completely lose the plot of the prompt.
Exactly. And the empirical data shows that with the drop-and-leave method, without that vital rescaling step, the cosine similarities between the layer embeddings plummet rapidly as the data moves deeper into the network.
On the Wizard Math 7B model, at a 90% drop rate without rescaling, the cosine similarity of the embeddings in the deeper layers drops all the way down to 0.68.
The geometric structure of this signal is totally degraded. The model is essentially blind.
But when you observe the vectors after applying DARE's rescaling operation, the cosine similarity stays securely above 0.95 across all hidden layers.
Even when 90% of the fine-tuned parameters have been physically deleted.
In fact, the distributions of the cosine similarities in the final output layer are practically indistinguishable from the original dense model.
This empirically mathematically proves that the rescale step is actively and successfully preserving the structural geometry of the model's internal thought process.
Another crucial comparison we have to make is between DARE and the historical approach to pruning, specifically magnitude-based pruning, or MP.
Magnitude pruning is a classic, highly intuitive technique.
The logic seems perfectly sound to human intuition. If you want to make a network matrix sparser, you just look at the absolute scalar values of the weights.
Keep the largest ones because they must have the most influence on the output.
and delete all the tiny weights closest to zero. I mean, it makes intuitive sense. So why does simply keeping the biggest parameters completely fail in this context where DARE succeeds flawlessly?
Magnitude-based pruning fails in this specific context because it fundamentally misinterprets how distributed representations function within large language models.
MP operates on the assumption that small magnitude weights are simply unimportant noise, and large magnitude weights are the true carriers of knowledge.
But in reality, within these massively over-parameterized networks, thousands of very small weight updates collectively contribute a massive mathematical expected value to the final output of a layer.
By indiscriminately deleting the vast majority of the small weights and only preserving the massive outliers?
Magnitude pruning completely destroys the collective expected value of the vector embeddings. The resulting vectors become highly skewed toward the outliers.
When the researchers pushed magnitude pruning to high drop rates like 70 or 90% on these delta parameters, it completely wrecked the model's performance.
For instance, on the 7 billion parameter models, magnitude pruning's accuracy on the GSM-8K math benchmark drops effectively to 0.
The model loses all ability to reason.
DARE, conversely, maintains near-perfect performance. Because DARE utilizes uniform random selection combined with mathematical rescaling, it respects and preserves the collective distributed contribution of the entire continuous distribution of weights.
Rather than just obsessively anchoring the network to the largest magnitude outliers.
Exactly.
That is such a profound insight into the nature of neural networks. It is not about the loudest, highest magnitude voices in the vector space.
It is about preserving the collective whisper of the entire distributed network.
Now, this brings us to a part of the paper that I found absolutely mind-blowing. This raises an important question, and it directly touches on a massive, ongoing philosophical debate occurring in machine learning research right now.
The unlock versus learn debate.
Yes, regarding fine-tuning. What is supervised fine-tuning actually doing to the model's brain? Is it injecting new, robust, factual knowledge into the weights, or is it merely teaching the model how to appropriately format and route the vast reservoir of facts it already learned during its massive self-supervised pre-training phase?
The researchers cleverly used the mechanics of DARE to test this empirically. And the results of this specific ablation experiment are arguably the most profound contribution in the entire study.
The researchers asked a very simple, targeted question. What if we apply the DARE pipeline to the total fine-tuned parameters?
Meaning the pre-trained base weights, PLUS, the delta weights, combine into a single matrix.
Right. Instead of just applying it to the isolated delta parameters, if the model's capabilities are highly redundant everywhere across the board, it shouldn't matter where we apply the drop rate, correct?
Right. So if you apply the exact same DARE math, but you drop 10% of the total combined weights instead of 90% of just the delta weights, what happens to the model?
The model suffers an immediate catastrophic collapse.
The researchers tested this on the Wizard LM model. With just a minimal 10% drop rate applied across the total fine-tuned parameters, the model's score on AlphaKaival plummets from 67.2 all the way down to a staggering 8.56.
On the rigorous coding benchmarks, Human Evil and MBPP, the scores dropped effectively to absolute 0.
The model's intelligence is completely destroyed by a mere 10% reduction.
But we must remember the paradox here. We just proved we can effortlessly drop 90 to 99% of the delta parameters with 0 performance degradation.
So if dropping 99% of the fine-tune updates does nothing, but dropping 10% of the base weights destroys the model, what does this definitively tell us about the unlock versus learn debate?
It serves as incredibly strong empirical proof that supervised fine-tuning does not add dense, robust, new knowledge to the model.
It merely unlocks and routes knowledge that is already deeply inherent in the pre-trained base backbone.
The massive pre-trained base weights contain the core intelligence, the vast web of factual recall, the syntax, and the foundational logic.
And those base weights are highly dense and incredibly sensitive to disruption. If you drop even 10% of them, you shatter the core intelligence engine.
The manifold collapses.
The delta parameters, however, act merely as a thin, hyper-redundant formatting layer. They're simply an instruction manual sitting on top of the base model,
telling the core intelligence how to structure its latent knowledge into a specific output format, like a Python script or a conversational reply.
Because SFT is merely a surface-level formatting patch rather than a deep knowledge database, it is incredibly sparse in its information density.
Which is exactly why you can delete 99% of it with DARE and still attain the skill.
This confirms that all the magic, All the heavy cognitive lifting occurs entirely during the pre-training phase. SFT is just the lightweight key that unlocks the door.
That is absolutely wild to conceptualize. The entire fine-tuning industry is essentially just building highly redundant, lightweight formatting patches.
A humbling realization.
But before we get too swept up in the hype, we have to talk about the rigorous limitations. The authors were exceptionally transparent about this in the paper, and the community has been actively probing these boundaries.
This technique isn't infallible magic. It operates within strict physical limits based on vector geometry.
It does not work on every single model combination out there. What is the explicit boundary constraint that dictates whether DARE succeeds or fails?
The primary constraint lies in the magnitude of the L-infinity norm of the delta parameters themselves.
Okay, what does that mean in plain English?
The researchers conducted a thorough analysis of the failure states of DARE, and they found a strict mathematical threshold. The DARE operation works beautifully when the absolute values of the delta weights are very small. Specifically, when the vast majority of the weight updates stay within a tightly bounded range of positive or negative 0.002.
This incredibly small magnitude indicates that the SFT process only made minimal localized modifications to the pre-trained backbone's manifold.
Yes.
And under what specific training conditions do the delta weights exceed that strict 0.002 boundary and break the DARE pipeline?
They drastically exceed that boundary when a model undergoes continuous pre-training on new data distributions, rather than just simple instruction fine-tuning.
The researchers provided a perfect example using the WizardCoder Python 13b model.
They attempted to use DARE to extract the sparse delta parameters between WizardCoder and the original Lama 213b base model in hopes of merging it.
But the DARE pipeline completely failed. The coding performance on human eval dropped to 0 instantly.
When they investigated the matrices to understand why, they looked at the parameter values. The delta values for WizardCoder had skyrocketed, routinely hitting ranges around 0.03.
Which is orders of magnitude larger than the safe 0.002 threshold. Why were the parameter updates so massively divergent for that specific model?
Because of its lineage. WizardCoder was not just fine-tuned directly from Llama 2, it was fine-tuned from an intermediary model called Code Lama,
which itself had been continuously pre-trained on an additional 500 billion tokens of code-heavy data after the initial Llama 2 pre-training phase had concluded.
Exactly. That massive influx of domain-specific data fundamentally shifted the weights deeply and pervasively, moving the model's representations entirely off the original base manifold.
Therefore, the ironclad rule for DARE is that the models must be strictly homologous.
They must share an identical, immediate foundational starting point. You cannot use DARE to extract deltas or merge models if the target has drifted too far away from the base manifold through continuous pre-training.
The delta parameters must represent a light formatting touch, not a massive fundamental architectural rewiring.
That makes perfect geometric sense.
Yeah.
The models have to be closely related siblings derived from the exact same parent manifold, not distant cousins.
Okay, we have covered the historical state of the art, the incredibly elegant linear algebra of DARE, the staggering benchmark improvements showing active synergy, and the strict physical limitations regarding continuous pre-training.
It's been a thorough breakdown.
Now it is time for my absolute favorite part of the deep dive. It is time for our signature novel notions segment.
I'm always excited for the speculative extrapolations. Let's hear what you have.
Now, as a mandatory disclaimer to you, the listener, the ideas discussed in this concluding segment are highly speculative. They are imaginative extrapolations of the current research, and they are presented purely for entertainment purposes.
We are taking the empirical data from the DARE paper and pushing it to its logical, if somewhat outlandish, extreme.
Here's my pitch. Inspired entirely by the extreme sparsity and CPU merging architecture we just discussed, I call it decentralized edge swarm intelligence.
I am intrigued by the terminology. Walk us through the mechanics of the scenario.
Let's reconsider the fundamental operational properties that DARE has just unlocked. Because this technique allows for flawless synergistic model merging via simple arithmetic vector addition on standard consumer CPUs.
And crucially, because it doesn't require any access to the original massive proprietary training datasets.
The barrier to entry for manipulating and combining language models has effectively fallen to 0. We are no longer strictly constrained by giant corporate data centers hoarding thousands of GPUs.
Therefore, we could realistically see a very near future of true peer-to-peer model evolution happening entirely and organically on everyday consumer edge devices.
Imagine a global network of millions of smartphones, laptops, and tablets, each running a localized, highly efficient base language model.
Given the current trajectory of model quantization and neural processing units in mobile silicon, having a robust 7 billion parameter base model running locally on a phone is an entirely realistic, near-term starting point.
Exactly. The hardware is already there. Now imagine a user's phone, while it's sitting idle and charging overnight, uses a tiny amount of local private data to execute a highly specialized fine-tune.
Maybe it learns the exact specific syntax for a proprietary coding language the user needs for their niche job.
Or perhaps it fine-tunes itself entirely on the user's personal medical history to act as a hyper-personalized health monitor.
Historically, sharing that newly learned capability would mean transmitting gigabytes of dense matrix data.
But with this new pipeline, the phone's CPU isolates the delta parameters, applies the drop and rescale technique, and wipes out 99% of the weights.
The resulting skill patch is no longer gigabytes. Because it is 99% sparse, it compresses down to a tiny, highly efficient payload of just a few megabytes.
A highly compressed, mathematically robust parameter patch that aligns perfectly with the 0.002 boundary threshold and the extreme redundancy findings we discussed.
Because it is just a formatting layer, the information density is incredibly low.
Right, so now you have these tiny, highly potent, megabyte-sized intelligence patches. Edge devices could continuously, passively broadcast these skill patches to each other over Bluetooth, local mesh networks.
Or simply drop them into decentralized peer-to-peer repositories.
Imagine walking through a massive tech conference. Your phone silently and securely absorbs a dozen different coding syntax patches from the devices of the developers walking past you.
Because of DARE's zero interference property, your phone's processor simply uses task arithmetic to instantly mathematically add these sparse vector patches to your local base model without any catastrophic forgetting or performance degradation.
If we connect this to the bigger picture of algorithmic development, the technical mechanism grounding this idea is the combination of task arithmetic with DARE's complete mitigation of parameter interference within the high-dimensional space.
Because DARE mathematically ensures the delta matrices are overwhelmingly sparse and physically non-overlapping, you could theoretically layer hundreds, perhaps thousands, of these localized patches onto a single homologous base model.
What you are describing is a continuous, spontaneous, evolutionary algorithm occurring organically in the wild.
It completely bypasses the need for central corporate servers or massive retraining runs. It fundamentally shifts the paradigm of AI development from giant centralized monolithic updates controlled by a single entity to an organic, decentralized hive mind.
The global network of edge devices absorbs new cognitive traits instantly and continuously, adapting to localized data exactly like a biological swarm adapting to its environment.
And the most brilliant part of this architecture is its reversibility.
Oh, true.
If a specific user patch turns out to be misaligned or causes an issue or hallucinate facts, because the merge was just a simple static vector addition, the device can just arithmetically subtract that specific delta matrix.
It is completely non-destructive to the base knowledge. The open source community could create verified, decentralized repositories of these tiny bare patches.
Need your local model to instantly understand the nuances of 18th century French poetry. You don't need a new model.
You just download the 2 megabyte DARE patch from the swarm and add it to your model's weights in 3 seconds on your laptop CPU.
It fundamentally democratizes not just the use of AI, but the actual creation, distribution, and composition of advanced intelligence capabilities.
It turns every single edge device from a passive consumer into an active node in a global, decentralized intelligence network.
It is a highly provocative and inspiring scenario. And while the exact networking implementation of a continuous Bluetooth mesh swarm might be a few years out regarding infrastructure,
the foundational mathematics making it theoretically possible were literally just validated and published in this paper.
The empirical fact that Super Mario V2 hit #1 on the global open leaderboard using exactly this kind of lightweight offline CPU-based merging proves that the era of massive, monolithic, trained-from-scratch specialized models might be rapidly giving way to an era of highly modular, dynamically composable, and instantly shareable intelligence.
And that modular, instantly shareable intelligence is exactly why the entire machine learning community is talking about DARE this week. It is an absolute paradigm shift in how we view the physical architecture of learned skills.
It's been an incredible discussion.
We are going to leave you with that provocative thought about decentralized AI evolution and swarm intelligence to mull over on your own. As always, thank you so much for joining us on this deep dive.
Make sure you check the show notes for the direct link to the paper so you can review the incredible linear algebra and those jaw-dropping benchmark tables for yourself.
Until next time, keep exploring, keep questioning, and we will see you on the next one.